Okay, so let us start the session. So 18 ASC 304J is our subject code, the active structures. Okay, welcome to the very first class in the 5th semester. So I'm just showing a typical airplane, showing some primary structures like wing and fuselage, the empennage, landing gear, the power plant. The empennage consists of the horizontal tail plane and the vertical tail plane. So horizontal tail plane or the horizontal stabilizer we can call, and vertical tail plane or vertical stabilizers. These are the primary structural elements that are available in our, in the case of a typical aircraft. So here, I'm just highlighting the fuselage structure, a typical fuselage structure here. You can see here the various structural members and also named here. You can see that this is a structural member that runs along the length of the fuselage, longerons, or it is called as a longitudinal stiffness. Longerons are longitudinal stiffening members that runs along the length of the fuselage, and this is a strut. It's a strut, we call it as. And if you take here, you can see here the stringers. We call this as stringers. The size of the stringer is a little bit smaller than the longerons or longitudinal stiffening members. Here you could see some thick structural element which is known as bulkheads. So we'll see later what are the types of loads are subjected to for these structural elements. Now here the figure shows monocoque and semi-monocoque structures. So the basic functions of the aircraft structure is nothing but it has to transmit and resist the externally applied loads or simply applied loads so that it can provide an aerodynamic shape, and it has to protect the passengers, payload systems, etc. from the environmental conditions that are encountered during flight. So by keeping all these things requirements, all these requirements in our mind, which results in thin shell structures where the outer surface, or we call it as a skin of the shell, is supported by the longitudinal stiffening members, stiffening members, or longerons. And we call this as a transverse frames or rings or formers, so that it can resist bending, compressive, and torsional loads without buckling. So such type of structures are called as a semi-monocoque structures. If you come over here, the monocoque structures where the entire loads, has to be resisted by the skin alone. Skin alone. The skin alone must resist all the applied loads. So this is called as monocoque structure. Semi-monocoque, the stiffening members must resist the bending, compressive, and torsional loads. Here you could see. So such structures are known as semi-monocoque, while thin shells which rely entirely on their skins for their capacity to resist the loads is known as monocoque. So here you could see some typical wing structure where you could see the ribs provides the aerodynamic shape for the wing, and the skin and the fuel tank and the stringers that runs along the length of the wing or the span of the wing, the ailerons, wing tip, spar. Actually, spar will be located here also, front spar and the rear spar and wing flaps. Okay. So here we should also think that you see the wing flap can be deflected upward or downward, and the aileron can be deflected upward or downward. Think about the aerodynamic moments, that is the hinge moments caused that are imposed on the wing structure, how these hinge moments to be balanced. All these things a structural design engineer must keep in mind while designing a structure or choosing any material for design purpose. So coming to the introduction part, okay, for example, as I told you, a structural system or aerostructure is a device which can resist, carry, and transmit the externally applied loads to the neighboring structural members without causing any permanent deformations. That means it should not cause any permanent failure to our structure. So whatever problems we deal with or we discuss with, we should remember that we are within the elastic limit. That is, material has to obey Hooke's law. That is very, very important. We are not entering into the plastic region. Okay. Now, the structural component must be capable enough. For example, if you take an aircraft structural component, it is subjected to tension, compression, bending, shear, torsion, or any of these combinations. So, the structural component must be designed in such a way that it should be capable enough to resist the loads due to tension, compression, bending, shear, and torsion, etc. So most of the structural components, if you take the aircraft due to the weight penalty, so the aircraft must have a high strength to weight ratio or high stiffness to weight ratio, so which results that aircraft structural components must have a thin walled sections of different geometrical cross sections. So the different geometrical cross sections like a channel, a circular, rectangular, square, E section, Z section, I section, top hat section, angle section, and so on. Why it depends on the geometrical cross section means the geometrical cross section, the properties of the geometrical cross section is very, very important. It plays a vital role in the case of a bending because of the area moment of inertia. If you take a rectangle, I moment of inertia will be BD cube by 12, DB cube by 12, and so on. It keeps on going for different cross sections. So the geometrical cross sections, the properties of the geometrical cross section plays a vital role, and also the orientation of the cross section plays a role while placing any components to resist load in our aircraft. Now, the structural components can be of open type or closed type. For example, uh, it can be open type of section. For example, channel is a open section type, and closed section beam also sometimes. For example, hollow rectangular, hollow circular. This is the closed section beams. Okay, so these are subjected to axial loads, bending loads, shear and torsion loads, or combination of all these loads. And we are trying to find out whether open section is efficient in resisting torsion or closed section is efficient in resisting the torsion. Bending of beams. Okay, so bending of beams is very important criteria which to be learned and understood as of this. I mean, aircraft structure is concerned. In solid mechanics, we would have learned about the bending moment and the shear force, how to plot the shear force and bending moments, how to find the bending stresses, and so on. I'll just distinguish these two, solid mechanics and aircraft structures, what we are trying to explore here, what bending stress we have calculated in solid mechanics and what bending stress we are going to calculate here in aircraft structures. Now let us get into this bending of beams. Now, for example, let us take a structural member which is subjected to an axial load. Let it be tension or a compression, whatever it is. The stress produced will be direct stress, or stress is equal to load by area, and it causes an axial displacement or extension or elongation if the load applied is tension. Suppose if a load is applied so that it causes the beam to bend, here the situation is different. So when the loads are applied along the axis, that is the length direction, it produces direct stress and it produces axial displacement, extension or elongation. But when the loads are applied perpendicular to the axis of the beam, so that what happens? The beam will bend. So, if you take a simply supported beam, the load is applied, a vertical load is applied that is perpendicular to the axis of the beam will bend like this. We call it as a sagging. The beam is said to be under sagging or sagging bending moment, or bending moment produced due to sagging is a positive bending moment. Similarly, if you take here, you just apply a bending moment, that is negative bending moment at the simply supported ends. That is a counterclockwise at the left hand and clockwise at the right hand. So the beam will try to bend upward, which is nothing but the beam is said to be under hogging bending moment, which is commonly referred to as a negative bending moment. All these things we have to keep in our mind. So in the case of a sagging, you could see here the top surface is smaller when compared to the bottom surface. That means the top surface is subjected to the compression and bottom surface is subjected to tension, which is quite opposite in the case of organ bending moments. See here, in sagging, the upper surface of the beam must be shorter than the lower surface as the upper surface becomes concave and lower one convex. The reverse is true for loads which cause organ. Now let me take one example. It's a eraser, rubber eraser. I've taken a rubber eraser. Okay. So let me assume this width as B and this depth as D, for example, rectangular cross section. Okay. So let me hold this rubber. So with the left hand and right hand here. So left hand thumb here and left hand index finger here. Same way right hand here. And try to apply a pressure. Try to bend towards this. I mean towards our body or whatever it is. You just try to bend like this. What happens? The bottom surface gets compressed whereas the top surface gets elongated. That means the top surface is subjected to tension and bottom surface is subjected to compression. You think in a reverse way. If you're trying to bend the rubber in opposite direction, that is, you hold here and here, try to bend in this direction, so that you could bend very easily because of the moment of inertia. Because about this axis, BD cube by 12, about this axis, DB cube by 12, which one is more? BD cube by 12 is more in this case. So you have to apply a pressure or a force little bit harder to bend like this. Whereas the opposite direction, if you want to bend, means it would bend very easily because Ix, I mean the moment of inertia is dB cube by 12 for that case. So you could see here the upper fibers have been stretched and the lower fibers have been compressed. So the fibers in between, which are neither stretched nor compressed, the plane is nothing but the neutral plane, where the fiber is neither compressed nor elongated or stretched. We call it as a neutral plane that we studied in solid mechanics, and the corresponding axis we call it as a neutral axis, where the bending stress is zero. Very, 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 very important. Always the bending stress is zero at the neutral axis, whereas the shear stress is maximum at the neutral axis. These things you should keep in mind always while solving the problems related to bending stress and shearing stress. Okay. So this is what I was trying to say. We just rotate the eraser and so that its shorter sides are vertical and apply the same pressure with your fingers. The eraser again bends, but now requires much less effort. See the bending stiffness offered by the material and the orientation of the material, how it behaves with respect to the bending stiffness. So the geometrical cross section also provides stiffness, bending stiffness to the externally applied load irrespective of the nature of the material. So that's what I'm trying to say. It follows that the geometry and the orientation of the beam section will affect the bending stiffness. So now let us come to this symmetrical bending. What is the symmetrical bending? So symmetrical bending, for example, here I've shown a cantilever beam with some symmetric section. Let the cross section be, for example, a square or a rectangle or I section, whatever it is. And this is the expression, very familiar bending stress expression that we studied in solid mechanics. M by I is equal to sigma B by Y is equal to E by R, where M is the maximum bending moment, I is the moment of inertia, E is the Young's modulus, R is the radius of curvature, sigma B is the bending stress, and Y is the distance from the neutral axis to the element that we are considering, or to the outermost fiber. Okay, so we studied this and we call this sigma B the bending stress to be bending stress due to symmetric bending. What does it symmetric bending means? Now, for example, you could see here different cross sections. Doubly symmetric, channel, single symmetric. Each section is a single symmetric. So let me take a doubly symmetric rectangular or square section. So let me apply a load perpendicular to the x-axis. Let us take this case over here to the figure cantilever beam. If I apply a load P along y-axis, this P into the length P into L is the moment which will make or which will cause the cantilever beam to bend about x axis. So I can call this P into L as mx, which is the bending moment about x axis. So here this term will be mx by ixx, mx by ixx. Once this force makes the beam to bend, for example, the amount or magnitude of deflection, at this end and at this end, or all the four corners will be same. That means the beam undergoes symmetric bending. Symmetric bending. So once this load causes the beam to bend, what happens to the top surface? It gets elongated. That means it is subjected to tension. So I can call that moment as positive bending moment. In this case, I can call that moment as positive bending moment. Now take like this. If the bending moment is acting like this, okay, bending moment is acting like this. So let me bring this force here, for example, parallel to x-axis. P is the force into L. P into L is the bending moment about y-axis. Now P into L is nothing but My, which produces tension on the right-hand side and compression on the left-hand side. So the right-hand side gets elongated. Now I can call My as a positive bending moment. So you could think why I'm considering only this portion for I'm referring to the sign convention. Why not to the other side? So the derivation which we are going to see in future slides, we are going to consider the nature of the bending which produces tension or compression with respect to the first quadrant. Okay, the surface or a structure, if it undergoes tension in the first quadrant, the resulting bending moment is positive. If it is compression, means the resulting bending moment is negative. I'll explain more in detail in the upcoming slides. Okay. Now like this. Now for example, the load is acting like this upward. So now the load is acting upward, P into L, which is again the bending moment about x-axis. So this causes compression of the top surface. Now I can call this moment as a negative bending moment. And this yellow color arrow mark pointing right hand side, just transfer this load to your cantilever beam. If you try to bend like this surface is subjected to compression. So resulting bending moment is negative. Why I'm saying or why I'm insisting on this sign conventions? Because in my bending stress expression, we get the terms mx and my. If you make any mistake in sign convention in taking the values mx and my into my expression, the whole result of the whole answer will go wrong. That we need to keep in mind. So here you could see here the moment. We are applying the moment at the two ends. You could see the neutral plane or the neutral axis where the bending stress is 0. At this we call it as a sagging bending moment or a positive bending moment. Think in opposite sense, which is nothing but a orging bending moment. Okay. Now, bending assumptions. Always you need to remember one thing whenever you enter into structural related problems, either structural mechanics or the aircraft structures or solid mechanics or strength of materials, you should always remember, keep in mind that the material of the beam is linearly elastic, homogeneous, and it obeys Stokes' law. That is nothing but stress is always proportional to the strain. The first assumption is a familiar assumption which you could easily keep in your mind whenever you go for any interview and you can answer it. And in the case of a pure bending, as I stated already, the plane which remains as it is without undergoing any tension or a compression, we call it as a neutral plane or the neutral axis. And this is the expression for the pure bending stress. M by I is equal to sigma, P by Y is equal to E by R. E by R. Now, for example, we have seen about the symmetrical bending. Now, what does this unsymmetrical bending means? Now, for example, I've taken the same cantilever beam, same expression. Here at the bottom of the slide, you could see some unsymmetrical sections, angle section and Z section and unsymmetrical channel sections. And you could see here the unsymmetrical bending, when this unsymmetrical bending happens. Now, when I apply a load at some angle with respect to the vertical axis or with respect to the horizontal axis, what happens? You just transfer this load here, for example, Assume that P is acting here at an angle theta with respect to the vertical axis. P cos theta, P sin theta. So I'm getting two components, P cos theta parallel to y-axis acting vertically downward, causing tension at the top surface, and P sin theta acting along the x-axis towards the left-hand side, causing tension towards the right-hand side, which means that both the bending moments are positive. So what will happen if you think about the magnitude of P sin theta and P cos theta? Both are in different magnitude, different acting in different directions. The beam will try to bend as well as a slight twist, which is commonly referred to as unsymmetrical bending. Which is commonly referred to as unsymmetrical bending. So you should always keep in mind that any symmetrical section, let it be symmetric about both the axis or the single axis, when the load is applied parallel to any axis, either x-axis or y-axis, the beam will undergo symmetric bending only. And second point, where symmetric section is subjected to a load acting at some angle theta, means the resultant bending is always unsymmetric bending. And if you take unsymmetrical sections, for any unsymmetrical sections, the load is acting parallel to the axis or at some angle with respect to vertical or horizontal axis, the resulting bending is always unsymmetrical bending. Resulting bending is always unsymmetrical bending. So our ultimate aim in this chapter is how to determine the direct stress, due to these bending moments. That means due to mx and my, which is understood that it's nothing but the beam section undergoes unsymmetrical bending. Beam section undergoes unsymmetrical bending. Okay. Okay, so like this I've shown here all the different forces. Okay, for example, if I take this P case, a theta with respect to vertical here, for example, P cos theta, P sin theta. So P cos theta will cause tension at the top, P sin theta will cause compression in the right hand side. So compression means it is nothing but a negative bending moment. Tension means it's nothing but a positive bending moment. Always it is with respect to the first quadrant. With respect to the first quadrant. Okay, because we are going to derive the expression based on that only. Okay. Now here you could see the general loads. If you take any ball, I have taken arbitrary cross section. So this shows where in a ball all the forces are acting simultaneously. Here it is shown that the XY Z plane, which is plotted XY plane, this is the length of the bar, for example. This corresponding U, V, W are nothing but the deflection or the displacement in the respective directions X, Y, and Z. And this WX is the UD acting X direction, and this W suffix Y is the UD acting Y direction, and this capital letter SX is the shear force in X direction, and SY is the shear force in the Y direction, and this MX is the bending moment about X axis, and MY is the bending moment about Y axis, and P is the axial pull, and T is the torsion. So here the single simple figure demonstrates or highlights all the forces acting on a bar or any structure. All the forces it is acting. For example, if you put a cut here, if a cut in between, just to study the equilibrium of the forces, So here I have made a cut, and these are the loads, externally applied loads. So this is the externally applied loads. How to study the internal force setup when we make a cut here? You could see here this side, all these forces should be opposite to the direction that are applied to the external loading. Here you could observe here T is anti-clockwise, here clockwise. See here bending moments, clockwise, anti-clockwise. Here anti-clockwise, here clockwise. Okay, both should be opposite. And here the moments acting on this section, this cut section, okay, it should be opposite to this. So both these magnitudes are equal and opposite to each other. So when I bring this section to this end, when I join these two, both the forces are equal and opposite and gets cancelled each other. Hence, the entire system is in equilibrium. Okay. Now let us come to this force system where I mean the bending moments are shown in a plane. Bending moments are taken in a plane actually.